Alright, hi everyone, welcome to my channel, City of Electrons. So in this video, we are going to talk about the three-phase induction motor example. So last video we worked example 1, and this video we'll do it work this. We are going to work with example 2. Okay, so the question is a three-phase 400 volt star connected induction motor has a star connected rotor with a stator to rotor turn ratio of 6.5. The rotor resistance and standstill reactance per phase are 0.05 ohms and 0.25 ohms respectively. What should be the value of the external resistance per phase to be inserted in the rotor circuit to obtain maximum torque at starting, and what will be the rotor starting current? This I is current, okay? The rotor starting current with this resistance. Let me just use current there instead. Starting current, current. Oh boy, current. Okay. Alright, the solution, we just took the data. So these values are from the equation. Okay, and I think it should be voltage, and I'll explain why we're using voltage instead of EMF here, instead of E2 here. Okay, V2. Now that's from this, okay, to 400 volts. Note that this is for 3-phase 400 volts. Then star connected induction motor. Okay, and star connected means for us to look for the single phase, or let me say when it is star connected, to get a single phase, what we'll do is the voltage divided by root 3. That will give you the voltage for single phase. Okay, then for the power it will be the power given divided by 3. Then of course the current remains the current. Okay, now yes, that's that. Then with a stator to rotor turn, please note that stator to rotor turn ratio, okay, equals 6.5. Note that K, which is transformation ratio, equals E2 over E1. E2 means the rotor EMF, and this is the stator EMF. And it's also the same thing as saying E1, which is stator current over rotor current. So this is transformation ratio. Rotor, stator, okay? 2 is rotor, 1 is stator, 1 stator, 2 rotor. So this is what K transformation ratio equals. Okay? So since we are giving stator to rotor, which means we are giving stator is 1 now, we are giving E1 to E2. That's stator to rotor. We are giving the inverse, meaning our K will be what? The inverse. Okay, our K will be K equals what? 1 over, what do we have there? 6.5. 1 over 6.5. Because we are giving what? Stator to rotor. Stator to rotor. So look at this thing. This is the inverse of this. Okay. If we were giving rotor, if we were giving rotor to stator, it would have been exactly what K is, which is E2 over E1. It would have been exactly what K is. That means K would have been just 6.5. But since we are giving the inverse, stator to rotor, we are using 1 over 6.5. Okay, I hope you get that. Now, so that's why we have K here equals 1 over 6.5. Okay, alright, so with that being said, move to the next thing. Oh boy. Alright, so at maximum, note that at maximum x2 equals r2. Okay, we put that in some videos for this. So let the external resistance be small r2. Okay, now this R2 per phase, that's the small resistance, or the external resistance to be added, it is our reactance minus our resistance. Okay, now that will give us 0.2, right? 0.2. Then our our current per phase is our E2 EMF per phase and Z2 per phase. But note, in this thing we have here is voltage we have, not EMF. Okay, to get our EMF we have to include, to get our E2 we have to include the transformation ratio, and our transformation ratio we have said that is what, 1/6.5. so this converts it to what, per phase. That's the still converts it to per phase. Then the times K, this thing should be V2. Should be V2. Okay, so in order to get E2, we are going to multiply in order to get E2, we are going to multiply V2 by the transformation ratio. And to get a single phase, we divide it by 3. So that's what's happening here. And we got this. Okay. So then at maximum, Z2 is this. So all we just did here was, this is for current, right? And of course from Ohm's law, V equals what? IR. So therefore, making I suggest formula, you have V over R. But based on the fact that we have reactance in this question, we have resistance and we have reactance, therefore we have to take the reactance into consideration, meaning we use impedance, because impedance contains, look at this, impedance contains both reactance and impedance is written like this. Okay, and then JX. Okay, so this is impedance. Of course, we use XX here because we said at maximum what? X2 equals R2. Okay. Alright. So all we did here, since we are looking for this current, all we did here is just look for the value of this and substitute it in here. Look for the value of this, which is this, we did, and substitute it in here. And that's how we got this. Okay. Please, in case I'm too fast, you can ask questions in the comment section. Okay, ask questions in the comment section. But most of these things we've done them in previous video. Most of these basics. So this is just example applying what we learned. So I will do example 3 straight away, which has 5 parts. So for example 3, a 1100 volts 50 hertz delta connected induction motor has a stator connected slip ring rotor with a phase transformation ratio of 3.8. Note, this one is also stator to rotor. Stator to rotor, meaning to be what? Like we said just now. Since we are giving stator to rotor, it will be what? And K is what? Rotor to stator. So this we are giving the inverse. We are giving the inverse stator to rotor, meaning it should be what? K will be 1 over this, that's the inverse. Okay, that's why we have K here like that. Okay, and of course this should be V2, which we have as this. Alright, and frequency 50 hertz we have as this. Let's continue. Now the rotor resistance and standstill reactance are this and this, which is this and this. Okay, per phase respectively. Neglecting stator impedance and magnetizing currents. Determine 1. Rotor current at start with slip ring shorted. So the first thing we are determining the rotor current at standstill. So this is of course rotor current. And note, at standstill slip equals 1. So we just solve like that because slip equals 1 at standstill. Okay, so I equals this over this. I explained how we got this formula using Ohm's law just now. Then, but E2 per phase, this should be V2. Okay, V2, which is what we have here. V2, what we have here. So we are multiplying it by the transformation ratio. Note that in this case we did not divide by root 3. Why? That's because this is what delta connected. For star connected, we have to divide by root 3 to get a single exit. We have to divide by root 3 to get a single phase. But for star connected, for delta connected, the voltage in the 3 phase is the same as the voltage in each phase, in a single phase for delta connected. Okay, so that's why we do not divide by root 3 here. Alright, so multiplying the voltage by the transformation ratio K will give us the E2. So we've gotten this. Now how about this? We'll come here, I will do that. We just substitute in the values R2 and X2. Substitute them in and we get Z2. Now we just bring this guy here and substitute in the values. What's this? Look at it. Put it here. What's this? Look at it. Place it here. Done. Okay, done. That's the A part. Then the B part says calculate the power factor as stand still. Power factor is cos phi 2. And I think we've done something like this in another previous video when we said this is the real part, imaginary part, and impedance, which is resistance, reactance, and impedance, and of course. Okay. So when we say power factor, which is cosine of the angle, so cosine is what? Adjacent to hypotenuse. So that's what we have here. Adjacent to hypotenuse. So what's this? The value, we already have it as this. So we'll substitute that in. And for this, we've calculated it already to be this. So you bring that in. And you get a power factor. As simple as that. The next question is rotor current at 4% slip. Now, slip is introduced. When there is slip, it means the motor is running. Based on the fact that slip is the difference between the synchronous speed and then the speed of the rotor. Okay, that is the difference between the speed of the magnetic field of the stator and the difference, and that of the rotor. You can leave the R out of it, but okay. Stator field speed, let me say it that way, and a rotor speed. This difference is the slip. And for us to have slip, it means the motor is what? Running. Okay? So, of course, same formula comes in again. But at running condition, E2 per phase, at running condition, let's say for now, since we are now looking for when it's running, let's just add this. Current when it's running, or when there is sleep. Okay, when there is sleep. And this when there is sleep. When there is sleep. Okay? So when there is sleep, E2 per phase when there is sleep equals E2 per phase multiplied by sleep. Okay? So this will now give us this new value here. And then for the impedance, when there is what? Sleep. When there is sleep, will now give us this. Okay, and for this guy, it will affect the reactance. So, reactance when there is sleep, it doesn't affect the resistance, but the reactance is affected. So when there is sleep, for our reactance, you multiply the reactance by the what? Sleep. Just like we multiply the E2 by the sleep. So that's what we have here. Z when there is sleep equals this remains the same. Here we introduce the sleep 0.04 multiplied by the reactance. That will give you our new impedance when there is sleep. Okay, so now our current when there is sleep equals this is the value for the E2 when there is sleep, when there is 4% slip, and then for impedance when there is 4% slip. This is it. So these are currents. Okay, when there is 4% slip. So how about our power factor when there is 4% slip? Again, we do this. Power factor when there is slip, our resistance, and then our impedance when there is what? Slip. Our impedance when there is slip is what? 0.015 divided by the resistance. That will give you this. Okay, so the last part, I think, that's the last part. What is the last part? So the last part is starting current. Starting current equals we are giving starting current as 100 ampere. Let me check for the question. I think we are asked to look for external. We are asked to look for the external resistance per phase required to obtain a starting current at 100 ampere in the stator. Wow. Take note of this. So 100 ampere in the where? Stator supplying lines. So that means this current is in the stator now, not rotor. Please. This current is where? Stator, and we say stator represented by 1. So this is the stator current. Note, this stator current, okay, in order to make use of this, the stator to rotor turn, there is a ratio K, and since this what happened just now? I only press Ctrl Z. Alright, so this is our stator current. Stator current. Let me shift. This is our stator current, okay, which is I1. Okay, so this is our stator current. Now our rotor current, this is rotor, yes, correct. Our rotor current will be our stator current multiplied by the transformation ratio. Now, why are we multiplying by transformation ratio? Look at this. Note, we said K equals what? I1 over I2. Same thing as saying K equals E2 over E1. But now we are dealing with the I, so let's work with the I. So these are I. This is transformation ratio. I1 over I2. So since we are given I1, how do we find I2? Very simple. Just make it subject. I2 means subject formula. That will give you what? I1 over what? K. Are we seeing it now? I1 over K. So I2 is I1 over what? K. But K now is what? 1 over 3.8. Okay? K is what? 1 over 3.8. We got that when we were taking our data now. K is 1 over 3.8. That means, of course, this thing will now mean we'll do this. I2 equals what? I1 times 3.8. When you take this like up. Okay? Hope that's clear. So that's how we are doing. That's why we did this. Saying I2 equals what? 100, which is I1, times what? K, which is 3.8. I think I should just put the 3.8 here. No. To make it a bit clear, let me do this. Because equal 1 over K. 100 over K, this is the correct way to write it. Okay? Then when you bring in the K, it will now be what? 100 over 1, 3.8. Yeah, this is the correct way to put it. Okay? So of course when this comes up, it gives you this. Perfect. Okay. Now, of course we calculated E2 in, I think, equation A, the A part, to be this. Alright? So since we are looking for that external resistance, all we are trying to do now is to arrange it in a way where we have our impedance as subject formula, because the external resistance will be found in the impedance. Okay, we'll get our total resistance from the impedance and then use that one to get our external resistance. Okay, now in case you don't understand what I just said, no problem. When I solve to the ending, I will explain backwards. Like I'm solving down, Then when I'm through, I will explain back up again, so you, in order for you to get everything well. Okay, so I believe you understand how we converted this one, I1 to I2 being this. So where E2 is this, right? So of course, from Ohm's law, E2 is what? I2 Z2, and then we just make Z2 subject formula, which is this. So from this we have gotten what? Z2 to be this guy. Now this is the point where we talk about the external resistance. So the external resistance, let's use small letter r. Okay, then our new resistance, okay, minus what? The old one, or you can say total resistance minus the from the old resistance. Let me just use total here. Okay, let me just use total here. Whichever way you use to represent it is okay. Alright, so let me just use total here. R2 total. Okay, so now with that being said, the new resistance, or the R total will be what? Good. The R total will be what? This equals this already, right? So all we did here was this, saying that to just make this guy subject formula. Okay, Z2 normally equals this now. So when you bring this square root this way, you have Z squared, R squared, D squared, and then you just make R2 subject formula by bringing x to this way. You now have Z2 squared minus x2 squared equals R2, and then when you square both sides, you now have R2 square root this. Okay, so sometimes I just like to call it new R2. Okay, now we've calculated Z2 already to be this. Wow, what a funny thing. This is negative. Okay, that's negative. So let's see if that's still correct. So I have a bunch of calculators. Let me just complete the process, but you can punch your calculator and ensure that's correct, and I'll do that right now. So just give me a second, let me confirm that. 0.7618 squared minus 0.25 squared. Okay, it's correct. So I just missed the sign here. Okay, sorry about that. Now, since we've gotten this R total, we are going to see the external resistance to be added. That's why I like to call it new sometimes. The external resistance to be added, oh, it's total, not new, is this one, R total, minus our resistance we had before. Okay, so this is our resistance we had before now. Let's check. Yeah, 0.012. Okay, so 0.012 minus this one, this total resistance. So I hope that's clear. Now I said I want to explain back, right? So we are in need of this, and this is what? The total minus what we have. Because if you remove what we have from the total, you will get the external. Simple as that. Okay, so all we did was to calculate for the total. Calculate for the total, which is this. And to find the total, we just do this. Okay, this expression, and we make this guy subject formula, and we get we make this guy subject formula. This guy will be inside. Where is it here? To be inside. But first, to use this guy, this number, okay, you have to know what this value is. That is why we had to do what? To make it subject formula in this place. Okay, and then calculate for it. But to calculate for it, we have to what? Know what I2 is. So that's why we have to convert I1 to what? I2 using transformation ratio. Yeah, so I just explained backwards. Okay, so I hope that's clear. Yeah, that's clear. So I think that's all. Yeah, this is all for this. I think think this playlist for now this will be all for it. So I hope you really benefit or you enjoy this series, the playlist. So yeah, this will be all for now. Like, share, subscribe, comment, click on notification bell, and I'll see you in the next. I'll see you when I see you. Okay, thanks for watching. Bye for now.